looks like it's about 18.3 centimeters where that occurred. So what is happening here, do we think? Where is the antinode? Where is the node? There's one of these that's important here.
The node is the water.
Why? So that you're saying the antinode at the here. Why are the antinodes be there? Why could the node be there and the antinode here?
That's in the water.
What?
Because that's in the water, you can't hear it.
And then what's in the water?
The sound.
Why is the sound in the water? Go.
Okay. Hi. Well, the antinode has to be at the opening because that's where we're able to create the vibrations from. We see an opening, and so.
Why can the node be there? Why? There's zero stuff happening at the node, right? The node was stationary. The antinode is where all the stuff is going on. And so the antinode better be on top here. So it looks a little bit like this. We're going to draw a transverse wave, even though we know sound is what kind of wave? Longitudinal, but it's easier to draw a transverse wave. So the sound, we're going to say at that particular frequency, which we call a harmonic. This is called the first harmonic. It's the first place we hear this happening. Starts off at a crest right here. This is, we'll call this point A, if you will. A.
Sure.
And it comes in as a crest, so it's going to start to approach its equilibrium. So I hit the water, further hit the water, then it's going to bounce off the water and exit as a trough. So point A is there. This spot here would be point B, which is that, and then point C would be here, which is going to be right there. So we end up with a node at the water where we have the equilibrium point happening. It hits the water inverse. There's essentially a fixed end. So inverse comes back out, and so you have a crest and a trough up there oscillating back and forth at the maximum frequencies. And so you end up at that point with your really loud note because you have the amplitudes going nuts up there. So that's how we get that to happen. Couldn't hurt.
I don't know, it's supposed to be straight or steeper.
They're supposed to be straight, they're supposed to curve. We'll look at a better picture in a second. They're supposed to kind of curve to a point together. But I'll look at another picture in a second. So knowing, let's do that now. Good idea. So here's a little applet we can look at. This doesn't show up real well, huh? Can I zoom in? What makes that applet bigger? A little bit. What's that? Applet's a little program that they can Java you can play with for physics. There's lots of them on the internet. They're very fun. So this is what we just drew here. We have one side open tube, and we're sending in some sort of wave to it. So it comes in, it's kind of curved there, hits the bottom, and curves back out. This is the first harmonic. You always have to have, as you guys have all very well explained now, always have an antinode at the opening, because that's where you want the maximum amplitude to happen. If you had a node at the opening, that wouldn't work. That's going to be quiet again. Once it gets loud, at the 18 centimeters, somewhere around 36 then, if you were it's the quietest, but now you have an antinode, or you have a node at the opening. You can't really get anything from that other tube. So this would be what we call the first harmonic. Comes in, back out, it's our antinode. Questions about that? The second harmonic would be the next time we would get an antinode at the opening. It's going to come in, and cross once, come down, hit the bottom, come back out, cross again, and give me an antinode right there. Make sense? Then third harmonic would be the same idea, but now it looks like that. There's your standing wave. Fourth harmonic, fifth harmonic. They're all using the same note, but taking different octaves. That's why different piano strings are different lengths, or give you the same note but different octaves. So going back to our drawing, knowing this now, can I find the speed of sound using?
No.
But so the wavelength is 18.3. Okay. Or a half or a fourth. Okay. Why? This, okay, so this should be a wavelength right there. 18.3 was from point A to point B, which I called this chunk right here. So I have 1, 2, 3, 4 of those. So this should be lambda over 4, 18.3. So we actually have an equation for this that looks like this. We can say that if you have an open-ended tube, closed and open-ended, we can say the wavelength for a certain harmonic is going to be 4 times the length of the tube to make that harmonic, divided by what harmonic you're at, which would be n in this case. So the wavelength in this case, this is the first harmonic, is just 4L over 1. If it was the second harmonic that we saw in the other picture, it would be 4L over 2, which would be just doubling it, 4L over 3, and so on as you went down the line. And you kind of see where that comes from in that as we go right down to the lowest one, this, you can tell it's a quarter of a wavelength. Go to the next one, now you have like 1.5 wavelengths. So you can see kind of where that keeps changing. The next one's then going to be 1.25 wavelengths and so on. So that's pretty exciting stuff. So that's our harmonic. So anyways, we want to try and compute the speed of sound. Now I know the wavelength. So this wavelength, what's that? Times 4. So our wavelength was 73 or 0.732 meters. Was lambda. So now what do I have to do? So I know the frequency I said, so I wrote it off here, it's engraved 440. The frequency is 440 hertz. And I know I said that earlier, I said that the speed is lambda times f. So 0.732 meters times 440 hertz. So 322, the speed of sound in 20-degree air is supposed to be 343, so we're pretty close. I found that today, most people are getting speeds around 300 to 310. I don't know if it's the humidity and temperature or how that exactly works, but the temperature of the air will affect the speed much as the density of the material does, and the humidity would also affect the speed, that would probably cause more friction if you have wet air particles versus light air particles or dry air particles, I would guess. That's really the thing that can't be here, I guess. Questions about how we do that? All right, your job, then, give you about 10 minutes to do this because we have one more thing I want to do today, is to take some tuning forks and some mallets and see if you can compute the speed of sound. I will just point out, there's some of them you'll get a bad answer. There's some of them, because our tube doesn't start until like 12 centimeters in the water. And so if your first harmonic occurs somewhere in these first 12 centimeters, you're not going to get, when you just do that equation we have, you're going to get the wrong answer. So you're going to, if that happens to you, that means you're probably on the second harmonic. You can adjust that, but I believe, if I didn't have to correct it earlier, if you stick between 600 hertz and 200 hertz for your different tuning forks, that won't be a problem. But if you go over that, then you're going to get first harmonic in this area we can't measure. Questions?
You measured the height by moving the inside tube up, and then what number did you look at?
There's the number off of here that was on the surface of the water. So you like look through the plastic.
Okay.
I had it against the wall so I could see where the water hit the tube.
So you put that one there and roll it last time.
Yes. Right? Exactly, yeah.
To get a wider one would be
I'm going to say yes. But it might have other consequences too. Well, no, the amplitude is determined by this thing. The source determines the amplitude. So the tube itself wouldn't affect the amplitude, I wouldn't think. I think a bigger one is going to make it, it's going to change, because the wave is going to try and get out of the tube, it's going to bounce up the sides, essentially. I think if I think about like a pipe organ, the bigger pipes are lower. So I think the size of the tube would affect the tone, or it actually affect the frequency of the note. Because you're going to have more room to bounce back and forth, giving you like longer wavelengths, right? Which is a deeper note. I think that's a good question. Not exactly sure. Do you know?